So we can't just use math and logic all the time. We also have to think about the reasoning behind whatever it is that we're looking at. Like I said with the homework, if you're talking about oil production, there really have only been, well, during my lifetime, there's really only been one time when oil production actually made a really physical, huge move, and that was during the 80s when we had the oil shortage. And that's because the group of Middle Eastern oil producers called OPEC decided that they weren't getting enough money for what they were sending out to the world. And so they all got together and they decided, we're going to raise the price of oil, and we're going to do it really high, and we're going to do it right now. And out in states like California, there were physically lines of people with their cars sitting at gas stations to get gas because there was an actual shortage. And at one point in Minnesota, gas during the 80s, mind you, got up to $2.28 per gallon. Now that was a really big deal because before that, the most we had ever paid for a gallon of gas was 99 cents a gallon. And all of a sudden, more than double. And then the rest of the countries got together and talked to OPEC and said, you know, you can't do this to us. We need to come up with something reasonable here so that you're getting a fair price for your oil, and yet you're not going to be hurting all of the other world's economies by doing this. Because when you raise the price of oil, you raise the price of everything. And that's because most of the food that we eat in the United States is trucked to us, you know, by the big vehicles, the big trucks that you see on the road. So everything goes up, and it really hurts the economies. So when you think about a model for oil, you can't make a quadratic model. Because if you make a quadratic model, you're saying that you believe that the price of oil is suddenly going to go up and it's never going to come back down again. And that doesn't make any sense. So while we use the math to say, here's how many points we have, let's subtract one, that would be our perfect math model, we also have to think about what it is we're talking about in the problem, if we have that ability. So this says problem 2 is about milk production in billions of pounds. Food production, the chart shows how much milk Wisconsin dairy farms produced in 1955, 1980, and 2005. Now, if we looked at this and we thought about what we did yesterday, we would say, hey, there's 3 points. 3 minus 1 is 2. We should use a quadratic model because it's going to fit this stuff perfectly. But it's the same thing here. This would be saying that we believe all of a sudden every calf that's ever born is going to be female and it will give milk. And somehow the world is just going to have milk coming out its ears and it's never going to come back down. We know that's not true. Milk production is reasonably flat. I mean, it really is. So we do have an upward slope with milk production, but it's not a huge change that we're going to see. So it really is better to use a linear model. So now with this one, it's up to us again. We could say, I don't want to use 1955, 1980, and 2005 in this model, and we could pick a 0 year if we want to. Let's see, what did the book do? So we can match that. The book, we're going to go ahead and use 1955 as the 0 year. It'll just make our calculations easier as we go through this. So if 1955 is our 0 year, we put 0 and 16.5 up here. And then we think, okay, 1980. How many years have passed from 1955 to 1980? 25. How many years have passed from 1955 to 2005? 50 years. There we are. While we're at it, Wisconsin is not the biggest milk producing state in the United States. Do you know what it is? It is California. Kind of weird. I think it's a little hot out there for all those animals, but there it is. So now we're going to put these in, but we're going to remember, hey, this is linear. You know, even if they hadn't told us this was linear, we should have reasoned to. The quadratic doesn't work for this model, and it just wouldn't be good. So I'm going to do second plus again and just clear everything I have in my list. You could certainly just do it individually if you want. But we've got 0, 25, and 50. And then we had 16.5, 22.4, 22.9, which doesn't sound very impressive until you remember this was all in billions of pounds of milk. That's in fact how dairy farmers get paid, is by the pound of milk, which seems odd when you're talking about a liquid, but that's how it works. So, stats, calculate, linear regression, number 4. And again, some of you will have to scroll down quite a bit to get to calculate, but there it is. And I think I'm going to go thousandths this time. Because then we'll have everything. It'll be, you know, as close as we could possibly get. Now, was it a perfect fit? How do we know it's not a perfect fit? R is not 1, you know? But it's the best we can do with a reasonable model for milk production. So our R here is approximately 0.9 if we do a little bit of rounding. So it's not perfect, but it's a lot better than a quadratic model. It definitely is. So there is our linear model. Now, use the model to estimate milk production in the year 2000. Okay? What should we use for X for 2000? Yeah, 45, because remember this was years since 1955. So if we take 2000 minus our 1955, we're going to get 45. So we want to see what happens if X is 45. We've got a really nice model to put it into, so that's what we would do. We would let the calculator tell us what 0.128 times 45 plus 17.4 is. 0.128 times 45, all in there correctly, 23.16 billion pounds of milk. And there have been times in the history of the United States when milk farmers have dumped their milk. And they do that because they are protesting the price of milk. Because milk is another thing where we get that for way too little money. I mean, the production of milk, it costs a dairy farmer a lot to produce milk. And we pay a really cheap price for that. So it didn't work. You know, milk is still reasonably low, but they're just protesting that, hey, we don't get a lot of money for our milk. The Got It says, use that linear model and let's figure out milk production in 1995. So what should we use for X for 1995? 40. Well, that's not a big deal. In fact, I'm going to cheat a little, and I'm going to hit second enter and just go change this 5 to a 0. There it is, 22.52 billion pounds of milk. There it is. Now, one of the things I want to remind anybody that's in the 11th grade, you talked about extrapolation and interpolation when you took province stats, and that's important here. These two would be very trusted models, and the reason that we would trust these numbers is because the data that we had up here covered the years 1955 to 2005. So if we're trying to make a prediction about something that's inside these data points, which we were, that would be interpolation. And interpolation is good. It gives you a really good idea of what's happened because it's history. It's already recorded. You already know it's there. If we wanted to use this model for 2026, it would not be as reliable. And that's because we don't have any data out here for 2026. It would be guessing, and that's called extrapolation, which is definitely less reliable than interpolation. So interpolation, think about inter. It's the first 5 letters of the word. That tells us it's inside the data that we already have here. Very good model, very good predictions of how things are going to work. But if we go outside that and extrapolate extra, we're going to be outside that data. It's not going to be as reliable. So those are some other things that we deal with in Prob and Stats is once you get your answer, is it a decent answer or not? These were both very good answers. Both would work very well. So this one says in problem 3, we're going to compare models. The graph shows the quadratic model for milk production in problem 2. That's an issue. Because look at this model. It fit perfectly. Perfectly. But what is that model saying about milk production? At some point, apparently all the cows are going to die off or be unable to produce milk. That doesn't make any sense. Unless there's, well, a major catastrophe. That's not going to happen. So the graph shows that quadratic model, and the quadratic model obviously fits it exactly. And then it says, given that both models are good fits, which seems more likely to represent milk production over time? And that would be the linear model. So it's not just about the math. It's just not. You have to think, if you're given information about where the data is coming from, you have to use that to think logically. So if 4 data points were given, would a cubic function be the best model for the data? So cubics look like this. They're asking us, would this be a better model for milk production than this? What do you think? Unless something major happens and all the farmers in the United States decide to dump their milk, this is not going to happen. I mean, this is generally the real life situation. And of course, at the end of the cubic, we're saying that you could produce milk forever and only have so much milk, it's going to keep piling up for us, which isn't the case. Because if it did, milk prices would drop so low that farmers would go out of business. So, no, a cubic would tell us that milk production is unlimited. Once you have too many cows, you run out of space for them to graze on, and then their milk doesn't get produced. So again, you have to consider what's going on behind the scenes in the problem. So always consider the source of the data when we're deciding on a reliable model. Not generally a good idea to just go get data off the, if you can, you want to collect the data yourself. But things that you could do, well, in this last example, there is a United States Dairy Association. You could get your numbers from the United States Dairy Association. In fact, we have a Minnesota Dairy Association. So you can contact them and get good numbers. Using physics or a geometric formula to generate data will produce an accurate mathematical model that can be used to make accurate predictions. Physics, you're going to see a ton of models for making predictions on things. And they're models that have been around for a long time and they know they're going to work. Geometric formulas, it's the same thing. They're formulas because we know that's going to work. Then it says other data, such as sales data, that's going to have less reliability because we're approximating any results that are outside the domain of the data. Here's what they're saying. Macy's is closing a ton of stores. It was just in the news this morning that Macy's is going to close lots and lots of stores. There's a lot of people on the job. And the reason they're doing that is because of predictions for the future. Now, I want you guys to think, because you've grown up at a different age than I have, about the number of times that you have actually physically visited a Macy's. How many people, raise your hand, have visited a Macy's more than 5 times in their to the Macy's 3 times in their lifetime. So you guys have been on the planet for quite a while. People are not going into Macy's anymore. What are they doing instead? Using the internet. Using the internet. So Macy's said, you know what? We're going to keep our internet business, but we don't need all these stores. We don't need them anymore. So they're making those predictions about the future based on what they see right now with people buying their products. Using a model within the domain of the data makes a prediction, and this is called, you heard me talking about this, interpolation. So if you already have data from the years that you want to investigate, that's really reliable data. You already have numbers for it. However, Macy's is doing the process of extrapolation. They're saying, you know, people were visiting our stores big time for years and years and years, and we were able to grow. But now people aren't visiting our stores, and it's going down more. And their prediction is that's not going to change. Somebody's not going to wake up one day and say, you know what, we should just all go to Macy's because it's just not going to happen. And that is the process of extrapolation, which is less reliable. So using a model outside the domain of the data to make a prediction is called extrapolation. They're trying to figure out what's going to happen in the year 2020. Well, we haven't been there yet, so we don't know. But from what they've seen a pattern, and that pattern tells them, hey, we shouldn't have as many stores. So these results are less and less reliable as you move away from the domain of your data. If Macy's is looking at the year 2050, they shouldn't be doing that. That's too far away. You know, whatever model you have right now, you have no idea what's going to happen in the future. You know, we don't know. Maybe it'll be like Star Trek. We'll all go over to a little box and we'll tell it we want pants and shirt. We'll hit a button and it'll produce pants and shirt for us. We don't know. So they can't make predictions like that. That would be extrapolation. All right, using interpolation and extrapolation. So interpolation inside the data, extrapolation outside the data. The table shows average annual consumption of cheese per person in the U.S. for selected years from 1910 to 2001. We are going to use, it says cubic regression, to model the data with a cubic function and then graph that with a scatter plot of the data. I'm not too interested in the scatter plot, but we'll take a peek at it to see how well that cubic regression fits it. And let's go ahead and use a 0 year here, but let's use 1900 as the 0 year. We could use 1910, but it'll just make the math a little bit easier. So this would be a 10, 40, 70, 75, a 95, and a 101. And we'll put that data in instead. It's a dairy stuff in there. They must have contacted the United States Dairy Council. Oh, there it is, United States Department of Agriculture. There we go. All right, so I'm going to clear my list. Get this in here as 10, 40, 70, 75, 95, and 101. And then pounds consumed per person. 4, 5, 8, 10, 25, 30. Per year, huh? I'd be a 4. Just that big on cheese. Cubic model. Stats. Calculate. Number 6. Y equals, well, look at that. E to the negative 5. Well, because they wanted a cubic model, let's move those decimal places over. So we're going to need 1, 2, 3, 4, 9 for our x cubed. Minus 0.00, move 4 decimal places with that one, then 0096 x squared plus 0.3106 x plus 1.8021. Our squared value is very, very close to 1, but it's not perfect. So what they want us to do is see the data and see how our line would fit it. So here's what we're going to do. We're going to do second stat plot, and we're going to turn that on. So second y equals, going into number 1, turning it on, making sure that my calculator knows it's in list 1 and list 2. But I need to change my window because this is not negative 10 to 10 business here. This one was 10 to 101, so maybe I'll do 0 to 105 by ones. And then my y's were from 4 to 30, so maybe 0 to 35. And graph. Looks like that. Now, I'm going to see what this line looks like on top of that. And to save time, I'm going to let the calculator put it in there perfect for me. So I'm going to hit Stats, Calculate, and I'm going to do cubic regression again. But this time I'm going to tell my calculator to store it for me. So this is where things are a little weird because some of you have the vertical one. I have to put in second, number 1, comma, second, number 2, comma. Because that tells my calculator to use list 1 and list 2. Yours probably already have those in there. And then you have to go down to where it says store. I think it's FREQ or something like that. What does it say after store? REG. Okay, so store REG. And go down to that one. And this is where we're going to hit variables. And that's just to the left of the clear button. And go into Y variables. So arrow to the right once for functions, number 1. And then we're going to store this in number 1, y sub 1. And when you hit enter, so for those of you with the vertical model, go down to calculate and hit enter. And if you hit y equals, you'll notice it put that whole huge mess right in there for us, which is really nice. And if we hit graph, it's going to put our cubic regression model over the top of that scatter. So scatter plot's there. So we modeled the data with the cubic regression and we graphed it with the scatter plot of the data. And now what they want us to do is use the model to estimate cheese consumption in 1980, 2000, and 2012. All right, everybody. How many years are we talking about from 1900 to 1980? 80. How many years from 1900 to 2000? 1900 to 2012. And now I'm going to cheat. Here's how we're going to cheat. This is all in our table. Remember, if we hit second table, that gives us all the years that we have here. But we can change our table so it doesn't start at 1 by using table set. So we're going to hit second window, and instead of having it start at 1, I'm going to have it start at 80. So now if I hit second graph and look at the table, there's my answer to the first one, 12.634 pounds of cheese. That's a lot of cheese per year. And then I'll do it again, but I'll start it at 100. So second window, that'll give you table set. And then second graph gives us the table, and that one has us at 29.445 pounds of cheese. Second window again and change it to 112. And we look at the table and we see that's 46.215 pounds of cheese. So we have the numbers that we would get if we used our cubic regression here model to talk about what's going on with cheese. So it says, in which estimate do you have the most confidence and which one do you have the least confidence? Two of these were interpolation, 1980 and 2000. And if I look at the chart, I notice there's data before 1980 and there's data after 1980. This would be the best one. Now, 2000 was also interpolation, so why didn't I pick that one? How many data points did we have that were past the year 2000? That's not a lot of data, you know. So it could be that that's going to be a good model because it's still interpolation. It's just that the other one had data before it and after it. And this one, our chart didn't go that far. 2012, if you take a look at the data up here, 2001 was the last year that we had. So this is extrapolation. And I want you to look at this graph again. Part of that is unrealistic. What's the unrealistic part there for cheese eating? It's going to keep going and keep going and keep going, especially when people find out how much fat is in cheese. There's no way that that is going to keep growing and keep going. It just is not going to happen. So we are very confident when we can use interpolation where there are points both before and after. Not so confident when we only have like 1 or 2 points on one side of it, but definitely it could be reliable. Maybe there's going to be a big cheese eating craze. They find out that cheese cures cancer or something, and you never know. But in reality, no. 40. Who's going to eat 46.215 pounds of cheese? That's eating a little less than a full pound of cheese every week. It's not going to happen. And this one says, if we did this with a linear regression model, then this would be better. But I hear doors closing. I'm just making me nervous. What's up with that? We have time. We've got the data already in there. Let's go ahead and do this. So now, linear regression instead. Let's go into y equals and let's kick out that cubic regression model. Let's clear that out of there. There's a lot of nastiness in there. So let's do stats, calculate, go down to linear regression, but we want it to store it this time. So again, I have to tell my calculator list 1, comma list 2. You already have that in there. Just go down to store, REG. And then we're going to put in that y variable again. So that is variables, y variables, number 1, enter. And then let's hit graph. Oops. Where are the stats? Linear regression. Oh, I hit the wrong one. Good gravy. I hit linear regression twice. So, linear regression. From list 1, comma list 2, comma variables. Y variables, function, number 1. Well, there we go. My R value, not so great, 0.84. And we could see that, you know, it doesn't even look like it's hitting any of the points there. So we have that, we've got it graphed. I would just make a quick little sketch of our scatter plot. And it says use this model now to estimate that consumption of cheese 1980, 2000, and 2012. So we're going to look at x equals 80 again, and x equals 100, and x equals 112 again. So a little more of that table set business. This would be 17.67 pounds of cheese a year. 23.067 pounds of cheese per year. And I might as well just arrow down since it's only 112. 26.305 pounds of cheese per year. And it asks the same questions about which of these would be most reliable, and we would give exactly the same answers as we did for the cubic regression. And that would be this one. We have points before and after. So this is the one that I would say is going to be pretty reliable here because it is interpolation, and it's pretty good interpolation. And while the x equals 100, yeah, it is interpolation, but there's only that 1 point on the upper side of it. And this one, obviously, the least reliable because it's extrapolation. this model really, I think, does fit linear pretty well. And if you're thinking, Cedar Home, do you really believe that people are going to eat more and more cheese every year? No, that's not my belief. We're going to have more people. You know, the world population is always growing, so there's going to be more cheese. So it's possible that that could go up. Cheese was one of the things that during the 80s, during the recession, the government gave it away for free. You know, you could stand in line and get a bag of rice and a great big thing of cheese for people that didn't have any money, and you know they were going to starve to death. So in the United States, we did that. For goodness sake, you know, don't think about those things happening here. 43210 me. How you feel about the interpolation, extrapolation stuff that we were doing, because we've already done the regression piece. Okay, it's a lot of really tough thinking for first hour, isn't it? Thinking about all these little things. Did you guys know that they had done that before? That they gave away free food in the United States for? Yeah, it was the 1980s were pretty bad. I think if it had gone on a couple more years, they might have actually called it a depression.